Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Imagine yourself lying on a soft meadow on a clear night, far from any city lights. The air is cool against your skin, carrying the faint scent of grass. Above you, the sky is a black, velvet dome sprinkled with countless stars. The Milky Way arches overhead, a pale river of starlight. In this quiet moment, you feel deeply connected to the cosmos. The same space that stretches between those stars also surrounds you. A gentle breeze brushes your cheek. It moves through the night and through the space around you, here on Earth. As you gaze upward in comfortable silence, more and more pinpoints of light emerge, a glittering mosaic against eternity. You realize that when you look at these stars, you are literally looking back in time. Their light has traveled for hundreds or thousands of years to reach your eyes tonight. Some of those stars may have already lived out their lives and vanished, yet their glow still journeys onward through the dark to greet you here and now. You feel the solid earth beneath you and know that it too is suspended in that great darkness, a small, warm world afloat in an ocean of space. Yet you are not afraid. The darkness above feels inviting, almost comforting, like a vast shelter. The endless sky, rather than making you feel insignificant, fills you with peace and wonder. In the silence, you sense with gentle certainty that you are a part of this grand universe. The starlight that falls on your skin, the space that cradles your body, the photons entering your eyes, all of it binds you to the cosmos. You close your eyes for a moment. Behind your eyelids, the after-image of the stars dances in little sparkles. You take a slow breath in, and as you exhale, you let any tension flow out of you and into the vastness around. There is room for all of it to dissolve. There is room for everything in space. The universe is so wide and forgiving that your own cares begin to feel lighter, quieter, soothed by the infinite calm. Now, in that spirit of tranquility, let us embark on a journey into space itself. The space around us, the space within us, the space that is the foundation of all things. We begin where we are, in stillness, in the darkness, in the quiet. The night is profound and motionless. Above, the stars shine as tiny islands of light in a vast sea of black. Space stretches endlessly between and beyond them. This scene feels serene and timeless. Nothing stirs. No breeze now, no sound at all, only a gentle hush, the natural silence of a cosmos at rest. It is as though time itself has paused. You can almost feel the depth of this silence, a soft, velvety silence that blankets everything. The emptiness around you seems to embrace you with a subtle, invisible presence. For ages, we humans looked at the night sky and found it peaceful, but also mysterious. What is this blackness between the stars? We used to think it was nothing, an empty void, an infinite vacancy. People spoke of the void and the vacuum as if it were a true nothingness. We even doubted whether a true vacuum could exist at all. Ancient philosophers imagined that space must be filled with something. Aristotle believed nature abhorred a vacuum. Later, scientists in the 19th century hypothesized an invisible ether filling space to carry light across the emptiness. But experiments showed no such ether was needed. Light moves through empty space itself. This was a remarkable discovery. The void can carry light, as if emptiness has its own solidity. It hinted even then that space is not simply an inert backdrop. For a long time, though, the common view of space remained that it was a passive emptiness, a gargantuan container in which the objects of the universe, planets, stars, galaxies, are scattered. We pictured space as a stage and the stars as actors upon it, with no real influence from the stage itself. If you removed all the actors, the stage would just sit there, blank and silent. We imagined that if you took all matter away, you'd be left with pure nothing, an absolute void, infinite and eternal. Over time, however, our understanding evolved dramatically. We learned that space is far from nothing. That black backdrop, that stillness and silence, is deceptive. Space has properties, a structure, a dynamic of its own. In the past century, every new discovery has reinforced this truth. Space can bend. Space can carry light and soundless vibrations. Space can stretch. It can even boil at the tiniest scales, flickering with unseen energy. What we once thought of as an empty stage is more like a participant in the cosmic play. Tonight, as you float in this quiet moment, the darkness around you is not dead or inert. It is the very fabric that connects and supports all things. Let's explore this step by step, gently and thoroughly, starting with one of the most profound revelations, that space and gravity are intimately linked. Beneath you, the Earth's mass is pulling you down, or rather, it's warping the space under your body so that down is the direction you naturally fall. Above you, the moon is held in its orbit by the shape of space around Earth. This understanding comes from Einstein's great insight in the early 20th century. Gravity is not a mysterious force acting across empty distance, but a feature of space and time itself. Mass and energy tell space how to curve, and the curvature of space tells objects how to move. In essence, matter sculpts space, creating valleys and hills in the fabric of space-time, and objects simply roll along those curves. What you feel as gravity, the weight on your back as you lie in the grass, or the pressure of your body against your bed, is actually space itself pushing you downward, guiding you along the curved lines it has formed around the Earth. To visualize this, imagine space as a vast elastic sheet spread out under the stars. If you place a heavy object on that sheet, say a bowling ball to represent a star or planet, the sheet will dimple, sagging inward around the weight. Now, if you roll a marble nearby, representing a smaller object like a planet, the marble will no longer travel in a straight line. It will spiral around the bowling ball, caught in the curve. In reality, Earth orbits the Sun because the Sun's mass curves the space around it, creating a sort of well that Earth is rolling around. Earth thinks it's moving in a straight line, and indeed it is, locally, but space itself is curved, so straight for Earth is actually a loop around the Sun. There is no gravitational force pulling Earth in a literal sense. Earth is simply following the path allowed by the curved space, like a ball rolling around a curved bowl. All planets, all moons, all orbiting bodies are doing the same. They are not tethered by invisible strings. They are skating along the contoured roads of space. Right now, as you lie still, you are held to the ground by this phenomenon. The mass of the Earth has curved space under you such that down points toward Earth's center. Your body presses into the ground because space is telling you to move that way. The ground pushes back and holds you up. Space does this quietly and continuously. You feel the effect as weight, but really, it is space-time gently urging you along a curved path that the solid Earth prevents you from taking. If Earth were not here, that curvature would extend unopposed. You would fall freely along a path through space toward where Earth's center was. All of this happens with no sound and no drama. Space does its work quietly. In essence, what we experience as gravity is the shape of space around us. Matter, like the Earth beneath you, tells space-time how to curve, and that curved space-time tells matter how to move. Gravity is not something that reaches out through space. Gravity is space. The stillness around you, in fact, is full of these invisible curves and subtle depressions wherever there is mass nearby. If you could see the geometry of space, You'd see gentle indentations around every tree, for even small objects curve space a tiny bit. Deeper wells around the mountains, and a huge well under your body, reaching to Earth's core. But space does its job so smoothly that you don't notice anything odd. You just stay attached to Earth as naturally as a leaf rests on the ground. This idea also means that when a massive object moves, it can create ripples in the fabric of space. Much like a stone dropped in a pond sends out waves on the water. Imagine two massive stars circling each other rapidly, or better yet, two black holes, extremely dense objects, spiraling together. They disturb the space-time around them so much that waves of curvature spread outwards. These are called gravitational waves, literal ripples of space traveling at the speed of light, washing through the cosmos. For a long time, we weren't sure these ripples really existed, but in recent years, scientists built instruments so sensitive that they could feel space-time tremble. When two distant black holes collided and merged, in a galaxy billions of light years away, our detectors on Earth quivered ever so slightly. Space itself stretched and squashed by a tiny amount, far smaller than an atom, as the gravitational wave passed through. We heard the universe whisper through space-time. It was as if the stillness briefly sang a faint melody. Think about that. We built a device that can sense the movement of space from events that happened billions of years ago in far-off corners of the universe. When we detected those waves, it confirmed that space-time is not just an abstract idea. It's a real, physical fabric that can carry vibrations. Space can ring like a cosmic bell, even though we cannot hear it with our ears. In September 2015, when those two black holes merged, the fabric of space around Earth oscillated subtly, and our instruments recorded the telltale chirp. It was a triumph of human curiosity and a profound validation of the idea that emptiness has structure. The silence of space isn't absolute. If you have the right ears, space can indeed be heard. What an elegant picture, space as an ever-present elastic medium, carrying both the weight of stars and the whispers of their collisions. In summary, matter tells space-time how to curve, and space-time tells matter how to move. Gravity is not a pull through some void. It is the gentle guidance of objects along the contours of space-time. All of this, the Earth holding you, the Moon orbiting Earth, Earth orbiting the Sun orbiting our galaxy's center, is happening because space itself is shaped by mass and energy. Our everyday experience of weight is actually our intimate connection to the shape of space. So, from the stillness of space arises what seems to be a force, but space has more surprises. We've talked about space's shape. Let's now consider its unity with time. When Einstein described gravity as the curvature of space-time, he was saying something equally profound about time. That time is woven into the very fabric of space. Out in this quiet night, space and time seem separate. You can point in directions, you feel time passing. But experiments and theories show that they are inextricably linked. If you move fast or sit in a strong gravitational field, your experience of time changes relative to someone elsewhere. Space and time together form a four-dimensional weave, and gravity is the bending of that weave. Consider that the passage of time on the surface of Earth is slightly slower than time far out in space, because Earth's mass not only curves space, but also warps time. A clock on a mountain, where gravity is a tad weaker, ticks a little faster than a clock at sea level. Likewise, a clock on a fast-moving spaceship will tick slower than one on Earth. This isn't science fiction. We've measured it with precise atomic clocks. Even the GPS satellites in orbit must correct for time running faster up there. Weaker gravity, so faster time, compared to ground. Otherwise, their positioning would drift. What we find is that space and time adjust together. If space is squeezed or stretched, time is also altered. They are two aspects of a single entity, space-time. Think of space-time as a fabric with both spatial threads and temporal threads interwoven. You cannot disturb one without disturbing the other. When the sun's mass curves space-time, not only does space get warped, but time runs a bit slower near the sun compared to far away. An astronaut near a massive object ages a bit less quickly than one floating in weaker gravity. This is called gravitational time dilation. Similarly, if you travel at a speed close to light, time for you will slow relative to those you left behind. There is a famous thought experiment. Imagine twins, and one goes on a near light-speed journey to a distant star while the other stays on Earth. If the traveling twin returns after what she feels was perhaps a few years, she might find decades or more have passed on Earth. Her clock and body experience time more slowly due to her rapid motion through space-time. This isn't just a story, it's a real effect, verified by many experiments with particles and precise clocks. All of this tells us that space and time are not the separate, absolute backgrounds we once assumed. There is no universal time ticking the same for everyone, regardless of their state of motion or gravity. Instead, every observer has their own passage of time, depending on how they move through space and how space is curved where they are. Two people reunited after following different paths through space-time will have experienced different durations. What an astonishing reality. Time itself is elastic, flexible, personal. So here, under the stars, when you consider a moment of time and a stretch of space, realize they are part of one four-dimensional continuum. Here and now are bound together. You cannot point to a location in space without also specifying the moment in time. Everything that happens in space-time. The unity of space and time frames all experience. Right now, your heartbeat and the position of the moon both have coordinates in space-time, and gravity is the geometry of that space-time linking the two. Space and time are fused like two threads of a single fabric. Move fast through space, and you skew your passage through time. Stand in strong gravity, and time for you will run a bit slower than for someone far away. This interplay might sound complex, but think of it this way. Space alone isn't the full stage, and time alone isn't either. Rather, events unfold in space-time. If you try to separate them, you lose part of the picture. Even this peaceful moment has a space-time coordinate. You, here and now, under the night sky. As you lie there, time flows a tad differently than it would if you were orbiting the Earth or sitting on the moon, because the gravity and motion differ. The differences are small but real. Space-time enfolds you, ensuring that your now and here are connected into the grand tapestry of cause and effect that makes up reality. The important takeaway is, space and time are one fabric, and gravity is the bending of that fabric. The stillness you feel includes both space and time quietly doing their work. There is a timeless quality to this night because space and time together create that sensation. In this eternal present, you are embraced by space-time, which gently carries you along the stream of time while holding you in the structure of space. We have journeyed outward to see that what we thought was emptiness actually shapes the cosmos, and journeyed inward to see time intertwined with space. But the rabbit hole goes deeper. We must now explore the nature of space at the smallest scales, far smaller than a grain of sand, smaller than an atom, where an entirely new picture emerges. One might expect that if you zoom into space closely enough, you would eventually find absolute stillness and uniformity, perhaps even true nothingness. But our current understanding, through the lens of quantum physics, says otherwise. On extremely tiny scales, space is anything but smooth and still. It is frothing and fluctuating, buzzing with ephemeral activity. Physicist John Wheeler poetically called this the quantum foam. To grasp this, imagine shrinking yourself down beyond the microscopic, beyond the level of atoms, to a realm billions of times smaller. If you could stand there, if the word stand even makes sense at that scale, the tranquil emptiness you perceive at our scale would vanish. Instead, you'd witness space seething with spontaneous eruptions of energy. Particles would blink in and out of existence like fleeting sparks. Distances and directions would blur as uncertainty reigns. In quantum physics, even what we call a perfect vacuum, completely devoid of matter and cooled down to remove all heat, is not truly empty. There is a fundamental jitter that cannot be removed. This is because the laws of quantum mechanics tell us that certain pairs of physical properties, like energy and time, or position and momentum, cannot both be known with infinite precision. There is a built-in uncertainty, and because of it, a vacuum cannot have exactly zero energy for all time. If it did, we'd know both its energy, zero, and that it stays that way, no fluctuation, forbidden by quantum rules. Instead, the vacuum seethes with what we call zero-point energy, a baseline, irreducible energy. What does this mean in practice? It means that empty space is constantly witnessing tiny particles flickering into being from nothing, then vanishing almost immediately. These are often called virtual particles. For example, a particle of light, a photon, might momentarily pop into existence, along with a counterpart, perhaps an electron-positron pair, borrowing energy from the vacuum for a brief instant. They appear, exist ever so briefly, and then annihilate each other, paying back the energy. All of this happens on timescales and distances so small we normally have no way to detect it directly. But it's happening everywhere, all the time. The space around you, between you and the next breath of air, between the electrons and nuclei in your body, between the Earth and Moon, is awash in these quantum fluctuations. On the scale of the unimaginably small, much smaller than an atom's nucleus, space-time would not look like a smooth sheet. It would look like a turbulent ocean surface in a storm, full of random waves, bubbles, and wrinkles, hence quantum foam. One moment, a bit of space might have slightly higher energy, sprouting a virtual particle-antiparticle pair. An instant later they collide and disappear, leaving a slight vibration of energy that then might spawn another pair elsewhere. Space at that level is a riot of spontaneous activity, an invisible, high-speed flickering that averages out to a seemingly smooth, stable whole at larger scales. We've even observed tangible effects of this quantum vacuum. If you place two metal plates extremely close together in a vacuum, just a few nanometers apart, they will experience a tiny force pushing them toward each other. This is the Casimir effect, and it happens because the quantum foam between the plates is slightly different from the foam outside. Certain virtual particle wavelengths can't exist in the narrow gap, so there is a tiny imbalance, fewer electromagnetic modes between the plates than outside. The result is a subtle pressure that nudges the plates together. In essence, the empty space between the plates has less quantum activity than the space outside, causing them to be pushed inward by the more energetic fluctuations outside. It's a small force. You'd need sensitive instruments to measure it, but it's real and has been observed. It's as if the vacuum between the plates is not nothing. It exerts a gentle push. This is a direct demonstration that empty space is never truly empty. The vacuum is alive with energy and possibility. In particle physics experiments, we also see clues of the quantum vacuum. For instance, empty space can briefly lend energy for the creation of particle pairs that affect processes like nuclear decay. The very fact that protons and neutrons inside atomic nuclei can change forms via quantum fluctuations involving ghostly particles is tied to vacuum activity. Even the stability of atoms and the patterns of atomic spectra bear the imprint of zero-point energy. So, as incredible as it sounds, the takeaway is that emptiness is not truly empty. It's an active medium. The stillness we perceive is actually a frenetic dance at microscopic scales. The vacuum is constantly borrowing energy here, giving it back there, in accordance with quantum uncertainty, Put poetically, even when nature whispers hush, there remains an undercurrent of subtle noise, a quiet fizz of existence and annihilation on the tiniest scales. The concept of nothingness has been forever changed by this discovery. Empty space is a cauldron of potential, a field of fields, a stage for ceaseless miniature drama. If you were to shrink down into that realm, as a moment's imagination, since physically we cannot, you might see space flicker with tiny flashes, the foam that Wheeler described. It wouldn't be placid or uniform, it would be dynamic and random. The notion of a sharply defined point in space might lose meaning, blurred by these fluctuations. We sometimes say space-time becomes quantum foam at the Planck length, about 1035 meters, far smaller than any particle. At that scale, the smooth geometry of space-time breaks down into something probabilistic and fluctuating. Let's take a different kind of imaginative journey to appreciate this. Inward, into the fabric of matter and space inside you. Envision shrinking yourself, as we did under the stars, but now not in distance outwards, rather in size. You diminish down past the scale of dust mites, past cells and their nuclei, past even viruses and DNA molecules. Now you are smaller than an atom. Ahead of you floats a single atom of carbon from your body. It appears enormous from your current perspective. You approach it like a tiny spaceship nearing a planet. The atom consists of a blurry sphere, that is the cloud of electrons orbiting the nucleus. As you draw closer, this cloud is mostly transparent. You realize the electrons are tiny points moving so fast, they form a diffuse shell. You dive through this wispy shell of electron probability and find yourself in the interior of the atom. Suddenly, you are in what seems like a vast cavern. It feels eerily similar to drifting in space between stars. It is dark and almost empty. You might even see a faint glow of energy fluctuations around. The quantum foam flickers here too. For a moment, it's as if you're floating in a miniature version of outer space, a huge volume with almost nothing in it. Ahead, after some distance, you see a tiny but brilliant object, the atomic nucleus. You move toward it. What before was the immense atom is now mostly behind you. All that's left ahead is that nucleus, a cluster of protons and neutrons tightly clumped. It's small, incredibly small. If the whole atom were a cathedral, the nucleus would be like a single grain of sand at its center, and yet, that grain of sand holds almost all the mass. You come right up to the nucleus. It's made of particles bound together, busy with internal motions, but you cannot linger. At this scale, forces are intense. You decide to zoom back out. When you return to human scale, you carry with you a profound appreciation. Inside every atom in your body, between the electrons and the nucleus, there are enormous stretches of empty space. In fact, nearly all of the volume of each atom is empty. The solidity of your body, of the ground, of this meadow, it's an illusion created by the electromagnetic forces of electrons repelling each other at those tiny distances. No two atoms ever truly touch in a physical sense. Their electron clouds push against each other first. Matter is a scaffold built on emptiness. It is astonishing. All the solid things we see around us are about 99% empty space. If one could magically remove all the empty space within the atoms of your body, compressing the electrons into the nuclei, you would shrink to a microscopic speck, smaller than a pinhead, yet you'd weigh the same as you do now. By some estimates, if we removed all the empty space from all the atoms of all humans on Earth, the entire human race could fit into a volume the size of a sugar cube. It sounds impossible, but it's because atoms are so vast compared to their tiny nuclei. Nature itself offers a demonstration. In neutron stars, the remnants of large stars, gravity crushes atoms so hard that electrons and protons merge, eliminating that atomic emptiness. A single teaspoon of neutron star material can weigh billions of tons. That's how much stuff was hiding in the empty space of atoms. When that space is removed, matter's true density shows. Fortunately, here on Earth, our matter stays spacious, our atoms intact with their generous voids inside. Take a moment to let that sink in. Solidity is an illusion. When we say an object, a rock, a chair, your own body, is solid, we're talking about the collective sense of touch that arises from trillions of atoms whose electrons resist being pushed into the empty space of one another. It is like a lattice of charged particles, and their mutual repulsion gives structure and firmness. But the structure is mostly empty space. We and the world we live in are made of a whole lot of nothing. It's a humbling realization. You are a being composed almost entirely of voids, shaped by forces and energy into the form you call you. In a very literal way, you are a small universe of particles orbiting each other in vast fields of emptiness. Now we have explored the microscopic character of space, the quantum foam and the atomic void. We've seen that even when matter is present, it's built on a framework of emptiness, and even when nothing is present, space is still far from idle or empty. The calm void of night harbors deep activity at tiny scales and comprises the majority of the volume of any solid thing. Space pervades every corner of existence. It is above us in the cosmos and within us in each atom. Let's step back out to the cosmic scale again. We've marveled at gravity and quantum foam and the space within atoms. But what about the shape of the universe as a whole? Does this infinite darkness go on forever? Does it curve back on itself like the surface of a planet? These questions have intrigued humanity for as long as we've looked up and wondered. Is space infinite, or is there some kind of boundary or loop? With modern science, we have attempted to measure the geometry of the universe. The answer isn't fully in, but so far it appears that on the larger scales we can observe, space is extremely flat and likely unbounded. By flat, we mean it follows the rules of Euclidean geometry, the sums of angles in triangles, etc., as far as we can see. If space had a noticeable curvature, we would detect distortions in the patterns of galaxies or the light from the early universe. The results? All measurements indicate that space is extraordinarily flat on the biggest scales. If there is curvature, it is so gentle that our observable universe, a sphere of about 93 billion light-years in diameter, doesn't reveal it. To use an analogy, Earth appears flat to someone walking a few miles because it's so large that the curvature isn't obvious at that scale. Similarly, the universe might be curved in some way, but on the scale we can survey, it looks effectively flat. What does flatness imply for the extent of space? It suggests that space could be infinite, extending forever in all directions, or it could be finite, but without boundary, like how the 2D surface of a sphere is finite area, yet has no edge, except extended to three-dimensional space. If space has positive curvature, like a 3D sphere, it would be finite in volume, and if you traveled far enough in one direction, you might eventually end up where you started, just as an ant crawling on a basketball eventually loops around. If space has negative curvature, like a saddle shape, it would be infinite and spread out with a different geometry. A flat universe, the simplest case, can be infinite and just go on and on. Current data lean toward flatness and therefore possibly infinitude, or a curvature radius so immense that for all intents and purposes it is infinite to us. From what we can tell, there is no edge to space, no wall where space ends. If it is finite and curved back on itself, going in a straight line could, in theory, bring you back to your starting point after an almost inconceivably long journey. We have looked for evidence of light wrapping around the universe, like seeing the same galaxies repeated from opposite directions, which could happen if space were closed and not too large. But we haven't found any such patterns. If the universe is finite and closed, it's far larger than the volume we can see. If it's infinite and open, it just has no end. In either case, there's no boundary that says, beyond here, there is nothing. Space, as far as we know, either goes on forever or loops back on itself. The observable part, what we can see, is certainly finite, but that's only due to the limited age of the universe and the finite speed of light. Beyond that observable horizon, we expect there is more universe, probably much more. We can summarize our findings here. The large-scale universe appears flat and unbounded. Precision measurements of the cosmic microwave background, the afterglow of the Big Bang, by satellites and telescopes have narrowed any possible curvature to be extremely slight. So, space is remarkably flat as best we can tell. It might truly be infinite. It might wrap around on a scale so huge we haven't detected it. Either way, for our observable domain, Euclid's geometry holds to a high degree. Parallel light beams do not meet, and the angles of a huge triangle drawn by, say, beams of light spanning billions of light years seem to add up to 180 degrees. This is a clue that the cosmos, on the whole, is not shaped like a sharp sphere or saddle within our view. If it is spherical, the sphere is enormous beyond imagination. If it is saddle-like, the curvature is so subtle that we haven't discerned it yet. In our contemplative journey, lying here under the night sky, it's awe-inspiring to realize we've been able to figure this out at all. By observing distant galaxies and the patterns in the microwave background, humanity has effectively used the universe itself as a giant ruler and protractor. We map the distribution of galaxies and notice that on large scales, they form a sort of cosmic web, filaments of clusters and superclusters surrounding huge, nearly empty voids. Those voids, expanses tens of millions of light years across with hardly any galaxies, highlight again how dominant space is over matter. Matter forms a delicate lace, and space is the vast expanse between its threads. The cosmic web shows that even on the grandest scale of clusters of galaxies, emptiness stretches out between them, making up the bulk of existence. Indeed, when astronomers survey the cosmos, they see that galaxies are not evenly spread. They line up in filaments and walls, with enormous voids between. Those voids are truly empty regions, aside from perhaps the stray hydrogen atom here or there. Some voids span hundreds of millions of light years with essentially no galaxies inside. Think about that. Such a volume is mind-bogglingly large, and yet nearly completely devoid of stars, planets, or light. Just tenuous gas and darkness. Those cosmic voids are, in a sense, pure space on the largest scale, a testament to how predominant emptiness is. The luminous matter, galaxies, clusters, outlines like scaffolding on the tapestry of space, but the vast gulfs between that scaffolding are space itself, pristine and quiet. Now, our understanding of space wouldn't be complete without touching on one of the greatest mysteries of the cosmos today, the fact that the universe's expansion is speeding up. We mentioned earlier that the universe is expanding like a rising loaf of bread, carrying raisins, galaxies, apart. You might expect, intuitively, that this expansion would slow down over time. After all, gravity is pulling galaxies toward each other. Indeed, for a long while after the Big Bang, the expansion did slow as gravity reined it in. But to astronomers' astonishment, in the last few billion years, the expansion has begun to accelerate. Galaxies are flying apart faster and faster. There is something in space, some form of energy tied to the vacuum itself, that is pushing the universe outward. We call this strange phenomenon dark energy. The name is just a placeholder, really, a label for our ignorance. It was discovered in the late 1990s when two independent teams observed distant exploding stars, supernovae, and found them dimmer, and thus farther, than expected. It was as if, over the billions of years their light traveled, the space between us and those supernovae had stretched more than it would have in a decelerating universe. At first, this result was met with surprise and a bit of skepticism. Could the expansion be accelerating? That was contrary to everything we thought. Even Einstein, long before, had considered a static, or at most slowing universe. But one by one, other evidence accumulated. Detailed maps of the cosmic microwave background and surveys of galaxy clustering both pointed to the same conclusion. Some kind of repulsive effect is at work on cosmic scales. By the early 2000s, the verdict was clear. The expansion of the universe is speeding up. So what is dark energy? In short, we don't know. It appears to behave like an intrinsic property of space. Like each cubic meter of vacuum has a certain tiny amount of energy that doesn't dilute even as the universe expands. If that's true, then as space expands, you get more vacuum, and thus more of this energy, causing expansion to push even harder, a runaway effect, though fortunately a very gradual runaway. Roughly 2/3 of the universe's total energy content today seems to be this dark energy. Only about 1/3 is in matter, mostly dark matter, plus a few percent normal matter like atoms. That means most of what's out there is this mysterious energy of empty space. It's dark because we can't see it or touch it. It doesn't emit light. And it's energy in the sense that it does work on the universe. It's causing space to swell. We sometimes describe dark energy as a negative pressure or an anti-gravity effect of the vacuum. It's as if emptiness itself has a springiness, a tendency to expand. Every bit of empty space gently pushes outward on itself. The effect is extremely weak on small scales. It's completely overwhelmed by local gravity or even the forces binding galaxies. But on the vast scale where gravity's pull has been growing weaker as galaxies get farther apart, eventually this subtle pressure took over and started accelerating the expansion again. The concept of dark energy reminds us how much we still don't know. It humbles us. We see its effects, yet the cause remains elusive. It could be something fundamental about space that we have yet to understand, perhaps related to that quantum foam energy we talked about. Those straightforward calculations of vacuum energy don't match the observed dark energy. That's a huge puzzle in physics. It could be a new field or fluid pervading the cosmos, or an adjustment needed in our theory of gravity at large scales. We gave it a name, but naming is not understanding. Dark energy is truly a question mark at the heart of cosmology. In essence, what we know is this: empty space isn't just inert nothing. It has this property that is making the universe fly apart faster and faster. The same emptiness between galaxies carries an unknown energy that currently drives the fate of the entire universe. Far from being an irrelevant void, space, through dark energy, will determine how the cosmos evolves trillions of years into the future. To put it succinctly, something latent in empty space, call it dark energy, is accelerating the expansion. The void has a sort of built-in push. This discovery is as dramatic as when we first learned space can bend. It tells us that space has a mind of its own, so to speak, a propensity not only to warp when mass is present, but to grow even where mass is absent. It's as though emptiness has a gentle heartbeat, steadily pumping the universe larger. So now we have seen space from two extreme perspectives: the microscopic, roiling with quantum fluctuations, and the cosmic, swelling with dark energy. We've also seen space permeating matter in atoms. It is clear that space is not a passive backdrop. It's dynamic and rich. Let's recap our journey so far in simpler terms. Gravity taught us that space is flexible. It can bend, fold, and ripple. Relativity taught us that space and time are united. Quantum physics taught us that space is restless at small scales. It's never truly empty. Modern cosmology taught us that space can expand and carries a mysterious energy in its very form. And everyday life and atomic physics taught us that even seemingly solid matter is mostly space inside. Now, with these insights, consider what space really is. It's not empty. It's the very medium of existence. Space is the canvas on which the masterpiece of the night sky is painted, and also the paint and pigments in that masterpiece. It is the medium through which light travels, and also an actor that shapes the story. By bending light, for example, as in gravitational lensing, where space curves around a massive galaxy cluster and bends the light of more distant galaxies into arcs. Space is the connector between distant objects, the silence that allows a conversation via light or gravity to happen across cosmic distances. Space is the stage on which all cosmic drama unfolds, and yet it is also an actor, shaping the plot with its curves and expansions. It is the ocean on which galaxies sail and the gentle tide that carries them apart. Space is a teacher of humility. It shows us that even what seems empty can hold unimaginable power and significance. It reminds us that absence can be potent, that silence can speak volumes. The stillness of space, which once seemed like nothingness, in fact contains the code that dictates the evolution of the entire universe. When we consider the scale of space and how much of everything is made of it, we might feel small, but there is comfort in it too. Space is a comfort in its constancy. It's been here since the beginning and will be here long after the end of all things. When we feel overwhelmed by our day, we can look up and remember how vast and enduring the universe is. Our worries shrink in the face of that perspective, not to trivialize them, but to soothe us with the knowledge that we're part of something much larger and older, where many troubles have come and gone under the eternal sky. Even our ignorance, like the mystery of dark energy, is a kind of tribute to how subtle and profound space is. It's astonishing to realize that only a century ago, we didn't know any of this. We thought the Milky Way was the entire universe, and we believed space was just an empty void that played little role. Now we've learned so much, that the universe is expanding, that space and time bend, that there are countless other galaxies, that space can erupt with virtual particles and drive cosmic acceleration. Each discovery has only deepened the wonder. Knowing that space can ripple and boil and propel galaxies doesn't take away the magic of the night sky. It adds layers of awe to it. The more we comprehend, the more we appreciate how extraordinary it all is. Finally, let's ponder one more speculation that stretches our imagination to the limit. The possibility that our universe's space is not the only space. Could it be that beyond the observable universe, or in dimensions or contexts we cannot see, there are other universes, other expanses of space-time, disconnected from ours? In other words, a multiverse. This idea is highly speculative, yet many scientists consider it plausible given certain interpretations of cosmology and quantum theory. One scenario arises from cosmic inflation, the extremely rapid expansion that likely occurred fractions of a second after the Big Bang. Inflation might not have ended everywhere at once. It could be bubbling continuously, even today, in distant realms beyond our horizon. Each bubble that inflation drops out would become its own universe with possibly different properties. Our universe would be one bubble among potentially countless others in a frothing metacosmos. To visualize this, imagine stepping outside our universe, a mind-bending thought, and looking at a larger sphere of reality. You might see an eternally expanding space like boiling water, with bubbles forming here and there. Each bubble is a universe, perhaps with its own galaxies and laws of physics. Ours is just one bubble that happened to inflate and then slow down, allowing stars and galaxies to form. Some bubbles might remain forever separate, carried away by relentless inflation in between. Others might occasionally collide, potentially leaving subtle imprints. People have even searched our sky for patterns that could be from a collision with another universe bubble, though none has been confirmed. In this view, reality is far grander than what we can see, a multiverse of universes. Another multiverse concept comes from quantum mechanics, the many worlds idea, where every quantum event splits reality into multiple branches. In that interpretation, there is a vast ensemble of parallel outcomes, parallel universes coexisting in a larger quantum reality. If true, There might be another version of you in a parallel world where some decision or event went differently. This is a different flavor of multiverse, more about layers of reality stacking on the same space rather than separate bubbles of space. But it underscores how space might be part of a much larger tapestry. Whether through cosmic inflation or quantum many worlds or other ideas, like perhaps a cyclic universe that periodically resets, the multiverse remains a hypothesis. We have no direct evidence of other universes. We may never have. It is a mind-expanding possibility, essentially suggesting that what we used to call the universe, meaning everything, might be just a tiny piece of an even vaster existence. If it's true, it's the ultimate Copernican revolution. Not only are we not the center of the universe, but our universe might not be the only one of its kind. Just one bubble in an endless foam. Such a concept can be daunting, but it can also be oddly comforting. It would mean creation is endlessly fertile. That reality tries every possibility, that somewhere, everything that can happen does happen. It also could provide an answer to that question of why our universe has the conditions it does, why the constants of nature are fine-tuned for life. If there are countless universes with varying conditions, we naturally find ourselves in one of the rare universes that is compatible with observers like us. In a multiverse, our hospitable cosmos isn't a 1 in a billion fluke so much as an inevitability among infinite tries. We should stress that the multiverse is still speculative. It's an idea, albeit one that arises from serious physics theories, but we have yet to find a way to test or observe it. It remains a tantalizing possibility on the fringes of our understanding. Whether true or not, just contemplating it broadens our perspective even further. It tells us that space, that fundamental thing we've been exploring, might come in an endless variety of forms across different universes. Perhaps some universes have more dimensions of space, or different kinds of particles, or maybe no matter at all, just endless empty space-time, expanding or contracting. The possibilities are endless. Even if the multiverse remains unproven, thinking about it does one certain good. It underscores just how precious our particular universe is. We have this vast cosmos to explore and understand, full of wonders like those we've discussed tonight. We might be essentially alone, with no other universes ever reachable, or we might be one among billions. Either way, our task and our joy is to know our universe as deeply as we can and find our meaning within it. Now, let us gently return to where we began, to the simple stillness of the night and the feeling of space around us. After journeying through curved space-time and quantum foam, across the cosmos and into the atom, we come back to ourselves, lying here under the sky, whether literally or in our mind's eye, quiet, at peace, and maybe a little wiser. The night is still as it was, but we are not the same. The darkness holds more meaning now. We can sense, behind the silence, the faint echoes of all those phenomena we've talked about. The whisper of space-time, the hum of the quantum vacuum, the faint pressure of dark energy, the quiet spaciousness within our very cells. The stillness around us resonates with the knowledge that it is not an empty stillness at all, but full of structure and story. Space is not empty. It's imbued with the fabric of existence. It connects everything to everything else. In this darkness, the light from distant stars travels. The space allows it to move at the fastest speed possible. The gravity of the Earth extends through space to tug on the moon. Fields, like the electromagnetic field, permeate space and allow radio waves, visible light, X-rays, all forms of light to propagate. Invisible geomagnetic fields from Earth reach out into space around you right now. Space truly is the medium in which all things exist, and through which all interactions occur. If it were somehow removed, all those interactions would vanish, and nothing could happen or even be. Consider some of the roles of space we've encountered. Space is the canvas on which galaxies paint their grand designs, and also the weaver that curves and folds itself to create gravity's effect. Space is the nurturer of structure. Its quantum fluctuations seeded galaxies, and its expanses gave them room to grow. Space is the arena of all history. Every event that has ever happened, from the birth of a star to the firing of a neuron in your brain, took place in space-time. Space is the ultimate connector. When you touch a loved one's hand, it's the space and electromagnetic force fields in that space, between the atoms of your hand and theirs, that communicates the pressure and warmth. Space is a teacher. It teaches us that what appears empty can be full, that absence can have presence. It is a guardian of the universe's secrets, hiding dark energy within itself, keeping the ultimate fate of the cosmos in its hands. And space will be the stage for the universe's far future. Looking trillions of years ahead, one can envision a time when space will be virtually all that remains. As the eons pass, galaxies outside our local group will drift farther and farther away, eventually vanishing beyond the horizon, their light stretched into oblivion by the expanding space. The night sky will grow emptier as distant stars disappear from view. Trillions of years from now, even the stars in our own galaxy will exhaust their fuel. One by one, they will wink out, leaving behind faint embers, white dwarfs, neutron stars, and black holes. These remnants will gradually cool and evaporate, in the case of black holes, via Hawking radiation, over an incomprehensible span of time. The universe will continue to expand and cool toward a state of almost complete darkness. In that far future, no new stars are born. No bright galaxies light up the sky. What remains is largely space itself. Vast, cold, nearly empty, studded only sparsely with subatomic particles and the fading whisper of photons from long ago starlight. And yet, through it all, space endures. The same fabric of space-time that was there at the fiery birth of the cosmos will still be there in that silent twilight eons hence. The stage persists even after the actors have left. Perhaps that will be the final chapter of our universe. An ever-expanding dark volume of nearly pure space, quietly extending into eternity. Perhaps, someday, quantum fluctuations within that nothingness might seed a new Big Bang, a new universe, a speculation in some cyclic cosmologies. But either way, the legacy of space is that it is the last cosmic witness. When all else has come and gone, space will still be here, silent and waiting, as it was in the beginning. Space is, in a sense, the alpha and omega of the universe, present at the start, shaping everything in between, and remaining at the end. Now, back to this moment. The night is deep and beautiful. The quiet around you, this gentle void, is the same entity we've been contemplating in all those extraordinary ways. Let that sink in. The empty air and space enfolding you right now carries the heritage of the entire cosmos. It carries the gravity that holds you to Earth. It carries the starlight that reaches your eyes. It carries the potential for future worlds and the echo of the very birth of the universe, a faint whisper of microwave background that bathes all of space, even now, at about 2.7 degrees above absolute zero, giving the night a slight warmth. This space around you is part of the same continuum that bends around a black hole and expands between galaxies and buzzes with vacuum energy. You are deeply connected to the universe through space. You always have been. It's impossible to be truly isolated because the fabric of space links you to the furthest galaxy and the smallest atom. When you look at the stars or simply breathe the night air, that connection only becomes more apparent. You are a child of space, born from stardust that coalesced in space, sustained every second by the oxygen and photons traveling through space. And ultimately, when you return to dust, your particles will drift in space again. Bask in that realization. You belong. You belong here in the universe, and it belongs in you. The boundary between you and out there is not a wall, but a porous membrane constantly exchanging matter and energy. You inhale the atmosphere, drawing in molecules that might once have been exhaled by ancient trees or dinosaurs, and ultimately originated in cosmic processes. You exhale, and your breath's atoms eventually mix into the sky and beyond. In a physical sense, you are never separate from the universe. You are always in communion with it. Take another slow, gentle breath. Feel the cool air fill your lungs, and know that even that simple act is an interaction with space. As the air spreads in your lungs, it's essentially molecules finding room in the internal space of your body, delivering oxygen to your cells across microscopic gaps. As you breathe out, you're releasing carbon dioxide that will travel through the atmosphere, maybe feed plants, maybe one day waft into the upper sky and beyond. Through you, the earth and space are linked. Now, you have permission to let go of all these thoughts if you wish. You don't need to actively think about curvature or quantum foam or dark energy anymore tonight. The knowledge is there, settled gently in the back of your mind, enriching the way you feel the night. You can simply relax in the feeling of it, the feeling of being part of this vast, ongoing cosmos. Above, the stars continue to shine, distant and silent. Around, the darkness remains calm and embracing. You might sense in your own body a mirror of the cosmos, the rise and fall of your chest like the expansion of space, the circulation of blood like galaxies drifting in their clusters, the neural flashes in your brain like tiny starbursts. In the stillness, you can almost feel the subtle humming connection between your life and the wider universe. You are safe. You are weightless and free. The quiet of space enfolds you like a warm blanket. Feel how the whole universe supports you in this moment. The ground beneath you, the air around you, the sky above. You belong here. You are part of all this. There is nothing you need to do right now except be. Just exist. Just rest. Inhale the stillness. Exhale any worry. Let yourself float on the calm of the cosmic ocean. You are safe. You are embraced by existence. You are at peace. No matter where you go, you carry this home of space with you. It was there at the first moment of your life. It sustains you each day, and it will remain long after we are gone. The stillness that surrounds you is the same stillness that cradled the young universe and that will hold the final stars as they wink out. You are truly home in this stillness. It is the cradle of everything. All the understanding we've gained about gravity, time, quantum foam, expansion, and so on, leads to a simple, profound truth. Space is not empty. It is everything. It is the foundation and framework of existence, and you are not separate from it. You are one with it. An expression of the universe, a part of space becomes self-aware. When you gaze at the night, the universe is gazing back at itself through your eyes. So rest now, gently, in the embrace of space. Feel the deep peace of knowing that you are held by the same darkness that carries the stars. The infinite extends around you, quiet and caring. Let go of any remaining tension. Let it fall into the vast well of calm that is space. Let your thoughts drift like gentle clouds across the sky of your mind. No need to chase them. They can float away into the darkness, leaving you calm and clear. You are safe. You are weightless. You are free. The endless silent universe enfolds you, and you belong to it. You are a part of it all, and it is a part of you. In this profound unity, you can release all fears and rest. The night is very quiet now. Around you, the earth sleeps, and the cosmos watches in patient silence. Feel your heartbeat slowing, peaceful. A tiny clock kept by space-time within you. Feel your breaths becoming soft and rhythmic, the same rhythm that pervades all of nature. There is no rush. Time flows at its own gentle pace. Space provides limitless room for your dreams to unfold. You are home in the universe. You are never alone. The space that fills your room, your lungs, and your heart connects you to the furthest galaxy and to the beginning of time. In this knowledge, you can truly rest. All is tranquil. All is as it should be. Stillness. The stars shine. The galaxy slowly turns. The universe breathes in and out on timescales far beyond comprehension. And here, in this quiet moment, you breathe softly, in unison with the cosmos. The stillness of space is within you and around you. Let it lull you into a deep and gentle sleep. Feel yourself drifting, weightless, on a calm, cosmic sea. There is nothing to fear in this dark. It is the same darkness that gave birth to the first dawn. There is everything to love in this silence. It carries the echoes of creation and the promise of eternity. You are safe, you are connected, you are at peace. Sink deeper now into the comforting dark. The universe holds you like a parent cradling a child. The ground beneath you, the sky above, all is one with you. Your mind is quiet, tracing the outlines of these truths with a final, drowsy sense of awe. What remains is not calculation or analysis, but a simple reverence for existence. In the grand sanctuary of space, you close your eyes, your breathing slow and steady. The boundary between yourself and the night dissolves. You are the universe, and the universe is you, a wave returning to the ocean of space. Rest now in that knowledge. Rest in the arms of the cosmos. Feel the profound stillness, the gentle, omnipresent support of space beneath you, holding you up as it has held up worlds and suns and galaxies. Let that stillness fill you. There is nothing more to do, no more striving needed. Just be. Just let yourself go, like a leaf floating on a vast dark pond, carried by the calm currents. Space will watch over you. It has always watched over everything. Your mind is calm. Your body is relaxed. The stars continue their silent vigil overhead, and you drift closer to sleep, carried by the same silence that spans the light years. The feeling of space, that stillness, that openness, that gentle cradle of all things is all around you, and it soaks into your very bones. In this moment, you are that stillness. There is no separation. Quietly, the universe whispers you a lullaby in the language of silence. It says, "You are home. You are home." Let yourself drift in this infinite peace, stillness, silence, space. The journey is complete. The knowledge is within you. The stillness is everything. You are a child of the cosmos, and the cosmos is kind. Feel its love in the quiet of the night. Space is not empty. Space is everything. And you, your atoms, your mind, your life, you are part of that everything. You always have been and always will be. In the great dark between the stars, there is comfort and belonging. In the stillness here, there is the embrace of the infinite. Be at peace, dear traveler of the universe. You are home in the stars and the night. The space around you is your space. The silence around you is your silence. Nothing separates you from the whole. You are safe. You are loved. You are one with the deep, eternal stillness of space. Rest now in that eternal stillness. Let the quiet carry you into restful sleep, as gently as a mother rocks a baby, as naturally as night becomes dawn. The universe holds you. Stillness, silence, sleep. Good night, child of space. The cosmos within and around you watches over you, now and always. Stillness, night on earth. The air is still and the sky is moonless and dark, spangled with stars. A soft band of milky light arches overhead, the Milky Way, our galaxy seen from within. Standing here, we gaze up and out at the universe. Each pinpoint of starlight that reaches our eyes is ancient. Each carries a story across time. Light is the great messenger of the cosmos. A photon departs the surface of a distant star and journeys for years, centuries, millennia through the interstellar abyss, finally ending its voyage in the pupil of an eye or the lens of a telescope. When we catch that faint glow, we are witnessing a memory. We see the star not as it is now, but as it was long ago when that photon began its journey. The night sky is a tapestry woven of past moments. Every glimmer is a relic of history, a tiny time capsule ferrying the past into the present. Each of those ancient photons is like a message in a bottle, cast into the cosmic ocean eons ago, and only now reaching our shores. Consider the stars scattered above. The nearest, aside from our sun, shines with light that left it a few years ago. Others are so distant their light set out while ancient civilizations on Earth were rising and falling, or even before humanity existed at all. And yet, here and now, their ancient light touches us. In this way, observing the galaxy is an act of bridging time. We collect the aged light of countless suns and piece together what it tells us. Observation is a kind of gentle time travel, not moving ourselves, but receiving echoes from distant years and distant places. On the clearest nights far from city lights, the Milky Way's band is breathtaking. It spills across the sky like a luminous river. To the unaided eye, it is a faint, cloud-like glow, but through that glow, we sense depth, as if we are peering into a crowded metropolis of stars, far away. Long ago, we could only wonder what this milky band actually was. Was it a path of souls, a backbone of night, a river of milk from a goddess? Indeed, the very name Milky Way comes from an ancient Greek myth that it was formed by milk sprayed from the breast of the goddess Hera. It took the curiosity and ingenuity of observers over centuries to unravel the truth. That band is the combined light of billions of stars, too distant and faint for us to resolve individually. We came to realize we are inside a vast disk of stars, a galaxy, and that the Milky Way's shimmer is our edge-on view of that disk. Imagine Galileo in 1610, one of the first people to turn a telescope to that soft blur of the Milky Way. In his small scope, the haze resolved into countless tiny points. The Milky Way was not a celestial cloud or fluid. It was composed of uncountable stars. This was a revelation, our first glimpse into the true nature of our galaxy. Later, astronomers mapping the sky noticed that those stars thickened in one particular direction, hinting that the center of this starry system lay somewhere behind the constellations of Sagittarius and Scorpius. Slowly, a picture formed in human understanding. We live within a flattened congregation of stars, like a great starry whirlpool. Our sun is but one star among many in this cosmic ocean. Now, as we stand under the stars, we appreciate something profound. We are inside the very structure we are trying to understand. Any map we make of the galaxy must be assembled from our viewpoint embedded within it. It's as if we are trying to discern the shape of a vast forest while being deep among the trees, or like attempting to read an enormous book while standing on one of its pages. We cannot step outside the Milky Way to see it whole. We must infer its form through careful observation and imagination. And so, we observe. We watch the heavens with every tool we can craft, collecting light in all its forms. We gather photons like alchemists, gathering whispers of truth. Each telescope, each detector, is an extension of our eyes, allowing us to see a bit farther, a bit clearer, or in types of light invisible to our eyes. With patience and ingenuity, we learn to decode the messages that light carries, the subtle shifts, colors, and timings that reveal distances, motions, and compositions. From tiny clues, we begin to perceive the grand structure that we inhabit. Think of the sky above as a grand mosaic. Each star's light is one tile in that mosaic. By studying those tiles closely, their color, their brightness, their position and movement, we start to discern the larger image they form. We realize that the faint band of the Milky Way is not uniform after all. It has structure. Brighter patches within it appear as soft, luminous swells, which we now know to be star clouds, densely packed regions of stars in our spiral arms. Dark gaps and notches, such as the Great Rift splitting the Milky Way in the summer sky, are not empty of stars at all, but shrouded by intervening dust clouds that block their light, creating black silhouettes against the glowing backdrop. Even our naked eye view hints at the galaxy's form. We see a bulging brightness toward one end of the band, toward the constellation Sagittarius, the direction of the galactic center, and a tapering, thinner glow extending around the sky toward the opposite end, the galactic anticenter in Auriga. The peoples of the southern hemisphere, for example, saw dark constellations in those dusty rifts, an emu in the sky, a great coal sack. Our ancestors spun tales of this band of light. Today, we understand it as the plane of our galaxy's disk, full of stars and shadowed by dust. As we drink in this sight, we find it humbling and wondrous. We are looking at our galaxy from the inside, using shards of ancient light to guide us. In that gentle glow lies everything: the collected radiance of distant suns, the imprint of interstellar clouds, the secrets of our galaxy's architecture waiting to be teased out. The journey to comprehend it is only beginning as we stand here, eyes upward and hearts open to the stellar chorus of light and time. But looking is only the first step. To truly understand this galaxy we call home, we need to measure and map it. How can we gauge the distance to those countless stars? How do we chart a landscape so vast while confined to a single speck within it? Over time, we learned to coax more information from the starlight, turning observation into a precise language. One of our earliest triumphs was discovering the method of parallax, the same effect you notice if you hold out your hand and close one eye, then the other, watching your finger seem to jump against far background objects. Our Earth, in its orbit around the Sun, provides a baseline 300 million kilometers wide. Every 6 months, as we stand on opposite sides of the Sun, nearby stars appear to shift slightly against the far background. It's a tiny, subtle wobble, imperceptible to the unaided eye, but with careful instruments we can measure it. By this minuscule celestial geometry, we determine how far away those stars are. The closer a star, the more it appears to shift. For the first time, the vast void between stars had a measurable scale. We learned that even the nearest stars are tens of trillions of kilometers away, billions of times farther than any voyage our species has ever taken, and more distant ones, hundreds or thousands of times farther still. The galaxy opened up in 3 dimensions, depth unfolding from what once was a flat panorama of lights. Imagine watching a particular nearby star through the year. In January, it's aligned just so with some distant background galaxy. By July, it has traced a tiny loop in the sky. That loop is the imprint of Earth's journey around the Sun, reflected in the heavens. From that trace, we triangulate the star's distance, like a surveyor mapping unseen lands from 2 vantage points. These measurements, painstaking at first, have now become an exquisite survey on a grand scale. Today, satellites with sharp electronic eyes measure parallaxes for over 1 billion stars, pinpointing their positions in space. With this technique, our stellar maps gained reliable depth. We began to know where we are and where other stars are in relation to us. Not just their direction, but their true distance in light years. Distance alone, however, is only part of the story that light can tell. The stars have motions of their own. They are not fixed jewels set in the firmament, but travelers orbiting the galactic center, each on its long journey around. Seen from our moving Earth, their motions across the sky are subtle and slow. But if we observe carefully over years and decades, we discern a drift. A star in the Big Dipper creeps forward. A bright neighbor slides subtly southward. Tiny changes in the constellations that over centuries will alter the sky's familiar patterns. This is proper motion, the apparent motion of stars across the sky as they sail through space. Early astronomers discovered a few nearby stars with noticeable proper motion, like Barnard's star, which moves faster across the sky than any other, about the width of the full moon every 200 years. Now, with modern detectors and long-term observations, we find that nearly every star has some motion. They are all participants in a grand dance, circling the center of the Milky Way at various speeds and angles. By measuring these motions for millions of stars, we begin to trace the currents and streams of our stellar city. We see which stars move together like schools of fish, perhaps born together in long dispersed clusters. We see which stars speed along faster or slower than average, which ones are plunging toward the center or flying out toward the fringe. The patterns of movement hint at the gravitational forces shaping them, drawing the unseen outline of the galaxy's mass and structure. As we map these stellar motions, we find, for example, that our Sun and its neighbors are all streaming in roughly the same direction around the galactic core, like autumn leaves caught in a slow eddy of wind. But some stars, often those outside the main disk or high above it, move quite differently, perhaps on steeply inclined or retrograde orbits that carry them far above and below the disk plane. These are clues to the galaxy's structure and history encoded in motion. We gather them eagerly, knowing each is a piece of the puzzle. Starlight carries yet more information hidden in its delicate spectrum, the rainbow spread of its colors. When we pass a star's light through a prism or a spectrograph, we see not just a continuous band of color, but a barcode of dark lines and bright lines. These are the fingerprints of elements within the star's atmosphere. Each chemical element leaves its mark by absorbing or emitting specific wavelengths of light. By reading this stellar code, we learn the star's composition, how rich it is in heavier elements forged by previous generations of stars. We learn its temperature and hints of its age. For instance, a star rich in metals, elements heavier than helium, is likely younger, formed after earlier stars seeded the galaxy with those metals. We also find, within those spectral lines, that many are shifted slightly from where they'd be if the star were at rest. Some lines are nudged toward the blue end of the spectrum, others toward the red. This is the Doppler effect, the same phenomenon that makes a siren's pitch rise as it rushes toward you and fall as it recedes. For starlight, a blue shift means the star is moving toward us. A red shift means it is moving away. Thus, the spectrum gives us the star's velocity along our line of sight, its radial velocity. Now picture this. We have parallax, giving us distance, proper motion giving us sideways movement across the sky, and spectral shifts giving us motion toward or away from us. Combine these, and for the first time, we can know a star's true motion in three-dimensional space. We can watch the galaxy's internal traffic, not just as a flat image, but as a dynamic, moving reality. With powerful surveys and observatories, astronomers have measured the velocities of millions of stars, compiling a vast catalogue of stellar motions. It is as if we have surveyed a great flock of birds in flight and traced each bird's path through the sky. From within, we map the Milky Way, not as a static snapshot, but as a living system, stars orbiting in the common gravitational field we all share. Each piece of data, a distance, a proper motion, a spectral signature, is a thread. Woven together, those threads create a rich tapestry, a model of our galaxy as it is, and, in a way, as it was, since even the motions of stars carry information about past events and the galaxy's evolution. We see, for instance, groups of stars moving in unison, perhaps born together in the same long-ago star cluster that has since dispersed. their common motion betraying their kinship across space. We find stars speeding unusually fast or slow for their location, hinting at gravitational perturbations or past encounters that have stirred the pot of the galaxy. Yet, even with such data in hand, mapping our galaxy from within remains an exercise in inference and imagination. There are still vast areas veiled to us, distances too great for parallax to reach directly, motions too subtle to detect within a human lifetime. We calibrate and extend our reach by using standard candles, special objects of known luminosity, such as certain variable stars or stellar explosions, which allow us to gauge distance by how faint they appear. We extend our velocity map by measuring not just individual stars, but also the bulk motion of star clusters and gas clouds. We are like explorers mapping a continent by combining local surveys, careful to stitch them into a coherent whole. It's a formidable challenge, but bit by bit, the dimensions of our Milky Way are coming into focus. Consider what we have learned through these patient endeavors. We know the Sun lies about 26,000 light-years from the galactic center, roughly halfway out along the Milky Way's radius. We know our galaxy is a rotating disk because we can sense the systematic motion of stars around the center. For example, stars on the inner side of the Sun, towards Sagittarius, are, on average, coming toward us, blue-shifted, as they overtake us on the inside track, while those on the outer side, toward Auriga, are receding, red-shifted, as we move away from them, indicating the entire disk spins. We know the scale of this rotation. The Sun and its neighbors are hurtling along at roughly 220 kilometers per second on this colossal circuit. Even at that immense speed, one full orbit around the galaxy, a galactic year, takes on the order of 200 million years. Our Sun has made only about 20 such orbits in its 4.5 billion year lifetime. When last it was in this same position in its orbit, the first dinosaurs were emerging on Earth and the continents had a different arrangement. On its next pass, 200 million years from now, who knows what life, or what changes on Earth, will see the galaxy from our Sun's vantage. To put this in perspective, if the Milky Way's rotation were sped up so that one galactic year lasted a single human day, then all of recorded human history would flash by in just a fraction of a second. Our lives are impossibly brief compared to the immense cycles of the galaxy. As we enrich our map with measurements, we also engage in an act of imagination. We convert data points into a mental journey. Let us embark on that journey now, to envision the Milky Way from our local neighborhood outward, using all we have learned. Through careful observation, we have gathered enough clues to sketch the grand design of our home galaxy. It is time to leave our little perch near the Sun and travel, in our minds, across the vast expanse of the Milky Way, guided by the light and motions we have collected, like navigators following a cosmic compass. Our journey begins in the quiet suburb of the galaxy where the Sun resides. Here, roughly halfway between center and edge, the stars are relatively sparse. We are in a minor spur or branch of a spiral arm. Not one of the Milky Way's big arms, but a smaller local lane of stars and nebulae. This feature is sometimes called the Orion Spur, our local side street off a major arm. Drifting outward from the Sun, we soon encounter one of the great spiral arms proper, the vast curving streams of stars and gas that wind around the galaxy. It looms ahead like a bright cloud on the cosmic horizon, a tremendous glowing avenue in space, studded with clusters of brilliant blue stars and embroidered with luminous nebula. In these nebulae, immense clouds of gas and dust, new stars are being born. We pass by a stellar nursery where hot, newborn stars light up the surrounding gas in pink and lavender hues. Nearby, a tight cluster of young stars shines brightly, their ultraviolet light causing the remaining gas of their parent cloud to fluoresce. This is the vibrant realm of the spiral arms, where star formation continually renews the galaxy. These spiral arms are the most striking features of the galactic disk. They wind outward from the center in a graceful spiral pattern, like the swirls of a giant pinwheel. Each arm is not a solid structure, but a kind of density wave, a traveling traffic jam of stars and gas. As this wave moves through the galactic disk, it compresses gas clouds and triggers star formation, leaving a wake of bright young stars that outline the arm's shape. We see these arms as glittering, starry ribbons. Along them live massive, short-lived stars that burn hot and blue and die young, so they never stray far from their birthplaces, thus tracing the spiral pattern in glowing neon blues. Meanwhile, older stars, like yellow suns and ruddy red dwarfs, are found everywhere, even between the arms, but they are dimmer and do not stand out as boldly to our eyes. Our own sun, a middle-aged yellow star, drifts in a quieter region between two major spiral arms, essentially in the galactic suburbs, far from any bustling stellar metropolis. We are situated between the nearby Sagittarius Carina arm, closer to the center, and the Perseus arm, toward the outer galaxy, in a calmer spur that branches between them. Generations of stars have come and gone here, long after the grand spiral pattern was established. As we continue our journey through the disk, we notice that it is indeed a disk, a relatively thin plane compared to its vast width. The Milky Way's disk is often likened to a cosmic frisbee or pancake, about 100,000 light-years across but only a few thousand light-years thick. In fact, the part of the disk where star formation actively occurs, the thin disk, might be only 300–500 light-years in thickness in the solar neighborhood, thicker toward the center. This thin disk is where most of the interstellar gas resides, where spiral arms shape the cosmic traffic, and where bright young star clusters light up the scene. It is flat because, as our galaxy rotates and evolved, collisions and angular momentum caused most matter to settle into this plane. Let's rise gently a bit above this cosmic plane to gain perspective. From just above the disk, looking down at a slight angle, the Milky Way's layout becomes apparent. We see that the Milky Way isn't just a single flat disk of stars, but has layers and structures. Above and below the bright thin disk, there is a sparser, thicker distribution of stars, appropriately called the thick disk. The thick disk consists of older stars with fewer heavy elements, spread over a greater range of heights above and below the plane. These stars move on orbits that are inclined relative to the plane and have a wider variety of paths than the stars of the thin disk. The thick disk doesn't contain the bright gas clouds or young clusters that define the spiral arms. It is more like a fossil record of an earlier epoch of our galaxy, or perhaps the result of an ancient merger that puffed up the stellar distribution. Its presence gives the Milky Way a faint extended glow when viewed edge-on, a kind of dim, broad corona of stars, through which the brighter thin disk is threaded. Returning to the plane, we journey further inward toward the galactic center. As we travel deeper toward the core, the stars around us multiply and crowd together. The sky grows richer with starlight. By the time we are halfway to the center, the star density is noticeably higher than in our neighborhood. We pass through another spiral arm, the Sagittarius arm, packed with stellar nurseries and clusters. Here, we see the remains of titanic stars that have lived and died. For example, a great supernova remnant, an expanding shell of gas from an exploded star, its filamentary tendrils glowing with the energy of the blast. Such remnants dot the interstellar space here, markers of past star deaths. The interstellar medium grows denser and more turbulent. Radio telescopes mapping this region reveal complex networks of cold hydrogen gas and molecular clouds, gathering like thunderstorms in the distance, awaiting the next trigger to form new stars. Moving nearer to the core, the spiral arms begin to converge and blend into a continuous, luminous mass. The distinction between individual arms blurs in a flood of starlight. We are entering the central bulge of the galaxy. This bulge is a huge, rugby ball-shaped, or peanut-shaped, concentration of stars at the galaxy's center. Here, the average age of stars increases. Many are old, swollen red giants that have shone for billions of years. The light takes on a warmer, reddish tint, dominated by these cooler old stars, and the interstellar gas is scarce. Most of it was long ago converted into stars or cleared out by supernova. In the bulge, stars are so numerous that the night sky from a planet deep in the bulge would be ablaze with thousands of stars visible to the naked eye, far brighter and more numerous than the sky we know. It would never get truly dark. When we observe the Milky Way's central bulge from Earth's skies, we are looking at this crowded hub from 26,000 light-years away, seeing it through dust that dims and reddens its light. The very heart of the Milky Way is a crowded, dynamic place. In addition to the swarming stars, there are mysterious radio sources, X-ray flashes, and high-energy phenomena. At the exact center lies something both invisible and immensely powerful, a supermassive black hole around which the entire galaxy revolves. We call this central dark object a black hole, but we might also think of it as the gravitational heart of the Milky Way. We have detected it indirectly by watching stars orbiting at fantastic speeds around an apparently empty spot in the bulge. Indeed, over decades, astronomers watched individual stars near the galactic center loop around this invisible point. One star completed a full oval-shaped orbit in just 16 years, reaching a mind-boggling velocity of over 5,000 kilometers per second at its closest swing by the unseen mass. These observations allowed us to pin down the mass of the hidden object, about 4 million suns, confirming that nothing but a black hole could concentrate so much mass in so tiny a space. Occasionally, this dark giant announces itself. If a stray cloud of gas wanders too close, the black hole's gravity rips it apart, and the infalling gas heats up and emits powerful X-rays before vanishing. For the most part, however, our galaxy's central black hole is quiet, a sleeping titan. In 2022, this inference was dramatically confirmed when astronomers captured a direct image of the region just outside the black hole's event horizon using a global network of radio telescopes. The result was a telltale ring of light, radiation from superheated gas orbiting the black hole, surrounding a dark shadow. For the first time, we saw the shadow of our galaxy's black hole, a sight that would have been unimaginable not long ago. What would it be like right next to that heart of darkness? If we could safely drift in the innermost region, we might see the fabric of space itself being warped by the black hole's gravity. We wouldn't see the black hole itself, it would be a void, but we might observe stars whipping around it in tight orbits and flashes as doomed material falls in. Around the black hole, within a few light years, is a nuclear star cluster, a densely packed cluster of stars orbiting furiously. Some of these stars are young and massive, paradoxically forming in the fierce environment near the black hole. How they came to be there is still debated. Perhaps their birth was triggered by the compression of gas streaming into the center. This cluster, along with the black hole, forms the dynamical hub of the Milky Way. If we could somehow hover above the galactic center and look down from far overhead, we would also notice that the Milky Way has a long, bar-shaped concentration of stars, stretching across its central region. Our galaxy, as it turns out, is a barred spiral. The central bulge is slightly elongated into a bar that extends on either side of the center for a few thousand light years. The bar rotates slowly, and it acts like a gravitational funnel, channeling gas from the outer galaxy inward along its sides. The spiral arms of the Milky Way actually emanate from the ends of this bar, rather than directly from a circular bulge. The existence of the bar was discovered through infrared observations, since the bar's stars are often hidden behind dust in visible light. In the tumult of the inner galaxy, the bar is another piece of the puzzle, a structural backbone supporting the inner spiral pattern. Gas flows inward along the bar and collects near the center, where it can fuel bursts of star formation or feed the black hole. Having experienced the brilliance of the galactic core, with its tightly packed stars and mysterious dark center, let us now journey outward again, this time away from the bright plane of the galaxy. We climb above the disk, moving perpendicular to the plane of the spiral, as if riding a beam of light straight up from the central region. As we rise, the full layout of the Milky Way's structure reveals itself in our mind's eye. Below us spreads the flat disk with its winding spiral arms, a whirl of starlight patterned by dark lanes of dust. We see the central bulge as a luminous peanut-shaped glow in the middle, with the straight bar cutting through it. The spiral arms trail off from the ends of the bar, curving gracefully around the galaxy's center. From this vantage point, the grandeur of the Milky Way is unmistakable. A barred spiral galaxy, one among billions in the universe, yet special to us because it is home. The combined starlight in the disk forms a hazy, glowing lens, crossed by the intricate silhouette of dust clouds. Those dust clouds, which from within appear as dark rifts, from above trace the spiral structure, particularly prominent along the inner arms and the bar, where concentrations of gas and dust are highest. Continuing farther up and out, the bright disk begins to shrink below us, contracting to a concentrated band of light. Now the surrounding environment grows darker and more diffuse. We have entered the stellar halo of the galaxy. The halo is a roughly spherical region enveloping the Milky Way, extending far beyond the disk in every direction. It contains only a tiny fraction of the galaxy's stars, so out here space is almost empty. The stars we do encounter in the halo are often very old, solitary wanderers, perhaps one here, another dozens of light years away, in stark contrast to the bustling crowds in the disk. Yet occasionally, we come across a grand sight, a globular cluster. Imagine floating into one of these clusters. Suddenly, the star density increases immensely, and you find yourself in a ball of hundreds of thousands of stars all around you, bound together by gravity. Astronomers have discovered around 150 of these globular clusters orbiting our galaxy. In a globular cluster's core, the night sky of a planet would be carpeted with countless brilliant suns, many more and closer than the stars we see from Earth's skies. These clusters are cosmic time capsules. Their stars are extremely old and metal-poor, lacking in heavy elements. They likely formed when the galaxy itself was young, before the disk fully developed, or even in small proto-galaxies that later merged to become the Milky Way. Now these clusters orbit in the halo, following long tilted elliptical paths that carry them far above and below the galactic plane. Scattered among the halo's sparse stars and globular clusters are also traces of past galactic meals, faint streams of stars rippling through space, the remnants of dwarf galaxies shredded by the Milky Way's gravity. We might not notice them with the naked eye, but our measurements reveal coherent trails, hundreds of stars moving together along the same orbit, stretched out across tens of thousands of light years. These are the ghostly footprints of galaxies the Milky Way devoured long ago, their stars now part of our halo, still traveling in the path of their original small galaxy. One of the most prominent of these streams comes from the Sagittarius dwarf galaxy, a satellite galaxy currently being torn apart. Its stars have been pulled into a long ribbon that wraps around our galaxy like a gossamer scarf. Only recently, thanks to exquisitely precise maps of star positions and motions provided by a space observatory scanning over 1 billion stars, did this substructure become crystal clear in our data, a fossil record of a cosmic merger, finally exposed by careful archaeology of the halo. The halo, then, is not a tranquil, empty realm after all, but a graveyard of sorts, and also a nursery of history, containing the debris of ancient mergers and the oldest survivors from the Milky Way's youth. Despite how far we have come, the influence of the Milky Way extends farther still. Encompassing all of this, the disk with its stars and arms, the bulge and bar, the stellar halo with its clusters and streams, is the galactic halo of dark matter. We do not see it, but we feel it in the motions of everything bound in the galaxy. The dark matter halo is enormous and massive. If we could somehow see it, it might appear as a vast, dim sphere enveloping the visible galaxy and extending hundreds of thousands of light years out. The visible Milky Way, the stars, nebulae and clusters we can photograph, is like the bright kernel at the center of an immense, unseen cocoon of dark matter. This invisible halo holds the galaxy together with its gravity. It is as if an unseen hand holds the entire galaxy in its grasp. Without it, the outer stars and gas would not be moving as fast as they do. They would drift away, unable to remain bound to the galaxy. In fact, astronomers deduce that around 85 to 90% of the Milky Way's mass must be in this invisible form of matter, leaving only 10–15% in all the stars, gas, and dust we can see. The luminous portions of the Milky Way are truly just the tip of a cosmic iceberg. The dark matter provides the additional gravity needed to keep the galactic disk intact and the outer stars tied to the whole. In our journey, though we cannot detect this dark component directly, we are always moving within it. It surrounds and permeates our galaxy, a silent partner in its evolution. Now, in our imagination, we have traced the structure of the Milky Way from our local neighborhood out to the farthest reaches, a shining spiral disk of stars with majestic curving arms, a central bulge, crossed by a bar, housing a supermassive black hole at its core, a surrounding halo of ancient stars and globular clusters, and mysterious dark matter, and an extended spherical cloud of dark matter encompassing it all. This is the architecture of our island universe, as we understand it today, gleaned from measurements painstakingly collected from our station inside the disk. It is an awe-inspiring vision, especially knowing that just a century ago, humans did not even know for certain that our galaxy was one of many. Only in the 1920s did we confirm that the Milky Way is indeed a galaxy of a particular size and shape, and that countless other galaxies pepper the cosmos beyond our own. The Milky Way itself is now estimated to span about 100,000 light-years from end to end, containing a few 100 billion stars. Our galaxy is immense, yet it is also just one member of a much larger cosmic community. For countless generations, our view of the Milky Way was limited to that hazy band of light in the sky and the visible stars around us. It is only in the last century that we have developed the means to extend our sight beyond the visible. Radio telescopes tuning in to invisible wavelengths, infrared detectors that can peer through dust, space telescopes above the blurring atmosphere, and more. Each new technology opened a fresh window onto our galaxy. With these tools, astronomers discovered a very different Milky Way, hidden behind the one our eyes perceive. A galaxy of radio glows and infrared heat, of X-ray flashes and gamma-ray bubbles. Consider the problem of dust. Invisible light, those dark rifts and patches that stripe the Milky Way, notably the Great Rift through Cygnus and Aquila and the famous coal sack in Crux, are caused by clouds of interstellar dust blocking the light of stars behind them. These dust clouds, though accounting for only a small fraction of the Milky Way's mass, loom large to our eyes because they obscure the stellar backdrop. Along the galactic plane, dust prevents us from seeing into the far distance invisible light. It creates a zone of avoidance where optical astronomy cannot penetrate. But dust's invisibility cloak has a weakness. It is far more transparent to longer wavelength light like infrared and radio. Imagine we could switch our vision to the infrared. The night sky would transform. Those dark dust lanes that cut the Milky Way's band would begin to glow softly because the dust itself emits infrared light, having been warmed by starlight. The veil of dust thins dramatically. Stars previously hidden behind dust clouds come into view. In infrared, one can peer straight through many of the dust clouds that block optical light. The galactic center, which to human eyes is hidden behind opaque dust in Sagittarius, now blazes forth in infrared images as a crowded, brilliant hub of stars. Early infrared sky surveys, pioneered in the 1960s and 70s, and dramatically improved with space telescopes in the 1990s and 2000s, revealed the central bulge and the long bar of the Milky Way clearly for the first time, confirming what radio and star count data had hinted. We see that the bulge is full of old, cool stars, dim in visible light but bright in infrared, and that the spiral arms are dotted with warm dust clouds in star-forming regions. The entire disk emerges in infrared as a continuous ring of light encircling the sky, no longer interrupted by dark gaps, a continuous Milky Way unbroken by dust. Now, let's shift to even longer wavelengths and open our radio eyes. In radio waves, the individual stars largely vanish from view. Stars emit relatively little radio energy, but other features emerge loud and clear. One of the most important radio emissions in the galaxy comes from neutral hydrogen gas. Every hydrogen atom in interstellar space can emit a faint radio signal at a wavelength of 21 centimeters. By tuning into that frequency, astronomers in the mid-20th century effectively heard the whispers of the Milky Way's vast clouds of hydrogen. They mapped the distribution of this gas throughout the sky. What they found revolutionized our understanding. The Milky Way's disk is traced by immense spiral-patterned streams of hydrogen gas, extending far beyond where most of the stars are. By tracking the Doppler shifts of this 21-centimeter emission, astronomers could chart the rotation of the galaxy and identify its spiral arms, even on the far side of the galactic center, which no optical telescope could ever see. Through radio eyes, the Milky Way's spiral structure was drawn out in detail, including portions of arms hidden behind the bulge. The zone of avoidance that plagued optical astronomy was no obstacle to radio waves. They passed through the dust and revealed that beyond the center, the galaxy continues in symmetrical splendor. In the radio view, we also see things our eyes never could. The flicker of pulsars, rapidly spinning neutron stars, sending lighthouse-like beams of radio waves. The glow of supernova remnants, where shock waves accelerate electrons to emit radio waves as they spiral in magnetic fields, and a diffuse background hiss of radio noise permeating the galaxy, caused by a combination of free electrons moving through magnetic fields and the distant multitude of unresolved sources. The center of our galaxy, in radio wavelengths, is actually one of the brightest sources in the sky. A strong radio source, called Sagittarius A, marks the location of the central black hole and its immediate surroundings. This was how the black hole was initially inferred, before the stellar orbits and images confirmed it. In radio waves, the Milky Way appears not as a single band of light, but as a complex structure. A band of emission from the disk, visible even in daytime with the right instruments, punctuated by bright spots, supernova remnants, pulsars, star-forming complexes, and with a bright, compact source at the center, the black hole's environment. Now imagine tuning our vision to shorter wavelengths than visible, into the ultraviolet. The scene shifts once more. The ultraviolet view highlights the youngest, hottest stars and the regions of active star formation. Many of the ordinary stars and red giants that dominated the infrared now fade into darkness in UV, as they are too cool to emit much at these energies. In their place, glittering like blue-white sparks, are the massive O and B-type stars, blazing fiercely with ultraviolet light. We would also see glowing nebulae, like the Orion Nebula, under the assault of intense UV radiation from these hot stars, appearing even brighter relative to the background. The spiral arms in UV are delineated strongly by these short-lived stars and their associated HII regions, ionized gas clouds. The galactic center's old stellar population would fade in UV, making the bulge much less prominent. But any regions of recent star formation or accretion near the center would stand out. The UV view, then, is a portrait of the Milky Way's vitality, emphasizing the sites of current starbirth and the presence of the hottest young stars. If we push to even more energetic extremes, into the realm of X-rays, the Milky Way we perceive changes almost entirely. Gone is the continuous sweep of billions of normal stars. Those stars are too cool and quiescent to shine in X-rays. Instead, the X-ray sky is dominated by rarer, high-energy objects, the end states of stellar evolution and violent cosmic events. We see the ghostly shells of supernova remnants filled with million-degree gas, glowing in soft X-rays. We see binary star systems where a neutron star or black hole is accreting matter from a companion. Such systems appear as point-like X-ray sources scattered through the disk, each a tiny beacon signaling where extreme gravity is at play. The dense star cluster at the galactic center lights up in X-rays due to hot gas and perhaps many small neutron stars and white dwarfs interacting. The supermassive black hole itself, usually quiet, occasionally flares, and those flares would make it a flickering X-ray source. We also detect a diffuse X-ray glow across the sky, especially toward the center and halo, indicating extremely hot, thin gas pervading the space around the Milky Way, likely a corona of gas heated by myriad supernova explosions, forming a kind of galactic atmosphere extending far into the halo. One of the most breathtaking discoveries of the past decade comes when we peer in the gamma-ray spectrum, the most energetic form of light. In gamma rays, much of the normal galaxy disappears. What remain are the signatures of cosmic ray interactions and exotic phenomena, and looming over the center, unexpected and huge, are the Fermi bubbles, two enormous lobes of gamma-ray emission extending tens of thousands of light-years above and below the galactic plane. Discovered by the Fermi Gamma-Ray Space Telescope in 2010, these bubbles are invisible in lower-energy light, but in gamma rays they glow as gigantic balloon-like structures. Their shape and extent suggest a powerful burst from the galactic center in the relatively recent past, perhaps a few million years ago, maybe a period of intense star formation, a starburst, or an active phase of the central black hole that drove energetic outflows. The Fermi bubbles reveal that the influence of the galactic center isn't confined to the disk. It has extended far into the halo. They are like a pair of cosmic chimneys, funneling energy from the nucleus out into space. Only by looking in gamma rays did these features become apparent, reminding us that each new way of seeing can unveil an entirely new facet of reality. Each of these different eyes on the galaxy, radio, infrared, visible, ultraviolet, X-ray, and gamma ray, tells a different part of the story. Yet they all describe the same Milky Way. Layer by layer, by combining these multi-wavelength views, we assemble a richer, more complete portrait. The dark, obscuring dust that frustrated optical astronomers becomes, in the infrared, a gentle glow and a transparent window to the distant reaches. The cold hydrogen gas that is invisible to our eyes comes alive in the radio, mapping out the spiral arms even on the far side of the galaxy. The ultraviolet shows us the high-energy heartbeats of the galaxy's ongoing starbirth, while the X-ray and gamma-ray views reveal the violent endpoints and energetic feedback that shape the Milky Way, from exploding stars to feeding black holes. We also begin to utilize cosmic messengers beyond light itself. Detectors on Earth have caught fleeting blasts of neutrinos, ghostly subatomic particles, from a supernova in a nearby galaxy, and observatories are now listening for gravitational waves, ripples in space-time, that could emanate from neutron star mergers or other extreme events in our own galaxy. These new forms of seeing, neutrino and gravitational wave astronomy, are still in their infancy, but they hold the promise of yet further insight into the hidden workings of the Milky Way in the future.
Picture the experience of gradually shifting through these wavelengths as a kind of cosmic symphony for the senses. The Milky Way is playing multiple melodies at once. The visible light is the familiar tune, the majestic sweeping strings section full of rich harmonies, the billions of stars. The infrared adds depth, the lower woodwinds, an undercurrent revealing the warm glow of dust, and the smoother distribution of old stars behind the veil. The radio brings in the percussion, rhythmic beats from pulsars, the steady hum of hydrogen clouds, the crash of supernova remnants, outlining structure with a deep, resonant background. The ultraviolet is like a bright trumpet fanfare, highlighting the most energetic star-forming regions with its bold, high notes. The X-ray might be an electric guitar riff or a sharp violin stab, sudden, intense accents from rare, violent events. And the gamma ray is an almost unheard, ultra-high note, a subtle yet profound presence marking the galaxy's most extreme outbursts. When the entire orchestra plays together, we hear the full symphony of the Milky Way, each instrument contributing its part to a masterpiece far richer than any single wavelength alone could convey. Through multi-wavelength astronomy, the limits of our sight have been greatly extended. What once was a narrow, partial view, the Milky Way as a pale band to human eyes, is now a complex, multi-layered vision. The so-called zone of avoidance in the sky has largely been conquered. Infrared surveys reveal stars hidden behind dust. Radio surveys discover even distant galaxies lying beyond the Milky Way that were once obscured. Within our galaxy, no corner remains completely unknowable just because of dust. We have the tools to probe even the most hidden nurseries of stars. We can now map the structure of the Milky Way in its entirety, even where thick nebulae lie in the way. We can see the galactic center in its full glory behind the dust, witness star birth sites otherwise invisible, and detect the faint echoes of past eruptions that no eye could ever see. Still, each improvement in vision often reveals new mysteries. For instance, the discovery of the Fermi bubbles in gamma rays answered the question of whether our galactic center had experienced a powerful recent outburst, but it also raised new questions. What exactly caused these bubbles? A burst of star formation blowing a galactic wind, or a period when the central black hole devoured a large amount of matter and expelled jets? Why do they appear so sharp-edged and symmetric? We also found hints of smaller, microwave-emitting bubbles closer in, and X-ray chimneys extending from the center, possibly all part of the same story. Every puzzle we solve yields new puzzles to ponder. And there remain portions of the spectrum and other messengers, neutrinos, gravitational waves, where the Milky Way has more to tell us. Yet, taken together, the information we've gathered gives us a truly spectacular understanding of our galaxy. We have learned not only what the Milky Way looks like, but how it came to be and how it is evolving. This brings us to consider the Milky Way not just as a static structure, but as a dynamic, living system with its own history, a history written in the stars. The Milky Way, magnificent and dynamic as it is today, is also very old. Its present form is the result of billions of years of evolution, a story written in the motions and compositions of its stars. Just as a geologist reads layers of rock to uncover Earth's history, or an archaeologist studies artifacts to piece together ancient civilizations, astronomers have learned to read the fossil record of our galaxy. The clues are subtle. The motions of stars, their chemical compositions, their ages, their distributions in space. By deciphering these clues, we are uncovering the Milky Way's biography, how it was built, piece by piece, from the deep past to the present. One of the most telling clues is the chemical makeup of stars. When the universe began, in the Big Bang, it consisted almost entirely of hydrogen and helium, with virtually no heavier elements, what astronomers call metals. Heavier elements like carbon, oxygen, iron, and gold were forged later, in the hearts of stars and in supernova explosions. Each generation of stars enriches the cosmic material a little more with these elements. Thus, a star's metallicity, the fraction of its material that is heavy elements, serves as a kind of timestamp. An old star, born when few generations had lived and died before it, will be extremely metal poor, nearly pure hydrogen and helium. A younger star, born after billions of years of cosmic alchemy, will inherit a higher proportion of metals. Now, when we survey stars in our galaxy, we find a striking pattern. The stars in the halo and those in globular clusters are generally very metal poor. They contain only tiny traces of elements like iron or calcium, maybe 1,000th of what the Sun has. These stars are fossils of the early Milky Way. They formed at a time when the galaxy, or its precursor fragments, had just begun forming stars, when only a few supernovae had seeded the environment with heavy elements. Some of the halo's metal-poor stars are among the oldest ever found, nearly 13 billion years old, dating back to within a few hundred million years of the universe's beginning. Some are so pristine in composition that they probably formed directly from the primordial gas enriched by only the very first stars, which were themselves long since gone. In their atmospheres, we see the faint chemical echoes of those first stars. These ancient stars wander the halo, individual embers from a time when our galaxy was in its infancy. In contrast, stars in the thin disk, like our Sun, tend to have much higher metallicity. The Sun contains about 2% of its mass in elements heavier than helium. That may sound small, but it's vastly higher than the metal fraction in those halo stars. It tells us the Sun is a relatively latecomer, born around 4.6 billion years ago, in a galaxy already enriched by countless earlier stars. By then, previous generations of stars had lived and died, seeding the interstellar gas with elements that would become the iron in our blood, the calcium in our bones, the silicon in the rocks of Earth. We truly are made of this star stuff. The oxygen we breathe, the carbon in our cells, all were forged in stellar furnaces long before the Sun's birth. Each of us carries pieces of ancient stars within us. The thin disk stars, especially in the inner regions, show evidence of ongoing chemical enrichment. Even within the disk, we observe that older stars have lower metallicity and younger stars have higher. It's as if each new generation of stars inherits the ash of previous generations, the heavy elements they produced, making each successive generation a bit richer in metals. Between these extremes lies the population of the thick disk and inner halo, which often have intermediate metal content and unique chemical signatures. Many thick disk stars have an enhancement in alpha elements, like oxygen, magnesium, relative to iron, suggesting they formed rapidly from gas enriched mostly by short-lived massive stars, which produce lots of alpha elements in supernovae before longer-lived stars had time to add more iron. This hints that the thick disk formed in a relatively quick, dramatic episode, perhaps triggered by a violent event. All these chemical clues tie into kinematic ones, how those stars move. Halo stars, as noted, often have very elliptical or inclined or even retrograde orbits, distinguishing them from the orderly rotation of the disk. The thick disk stars do rotate in the same overall direction as the thin disk, but with a bit more randomness. Some lag behind, some lead, and they have higher vertical motions. When we examine these patterns carefully, we find evidence that the halo itself might contain substructures, remnants of smaller systems. One clear sign emerged from our trove of Gaia spacecraft data. A large number of halo stars share a common motion pattern, moving on radial orbits, going out and back in, and possessing similar metallicities. They stand out as a coherent group amidst the halo field. Astronomers now believe that about 8 to 10 billion years ago, the Milky Way had a dramatic encounter with a smaller galaxy, a merger that delivered a huge influx of stars and dark matter. This invading galaxy was torn apart by the Milky Way's gravity. Its stars were strewn into the halo on those radial orbits, and its substance likely puffed up the pre-existing thin disk of the Milky Way into a thicker disk. The evidence of that event still persists in the motions and chemical makeup of stars, sometimes poetically dubbed the Gaia sausage or Enceladus stream, names given to that distinctive clump of halo stars. Such patterns in stellar motions remained hidden until modern sky surveys provided precise velocities for so many stars. Suddenly, this ancient collision stood revealed in our data, a fossil galaxy within the Milky Way's halo. In addition to that major merger, the halo holds hints of other, smaller mergers. We have found numerous star streams, long filaments and clumps of stars sharing common velocities and trajectories. Each stream is the stretched remains of some smaller object, maybe a dwarf spheroidal galaxy or a globular cluster that ventured too close and was pulled apart. The Sagittarius stream is one example we've mentioned, the ongoing disruption of the Sagittarius dwarf galaxy. There are others, the Helmi stream, the GD1 stream, and so on, each corresponding to a different accreted system. Even some globular clusters seem to belong to certain groups associated with past mergers. For instance, a set of outer halo clusters likely came in with the Sagittarius dwarf, while another set might have been part of the hypothesized Gaia Enceladus galaxy. By charting which clusters and stars came from where, we are assembling something like a family tree of our Milky Way. Which parts were original, which were adopted or acquired over time. Even within the disk itself, the stars carry memory of the galaxy's history. There are stars in the solar neighborhood that have much lower metallicity than the Sun, yet move in the plane. Perhaps they migrated here from farther out in the disk, or are part of the thick disk population. Some stars have peculiar chemical ratios that set them apart, suggesting they might have formed in an environment outside the Milky Way, say in a dwarf galaxy, and later been assimilated. The disk, especially the outer disk, contains subtle ripples and arcs of stars that might be the result of recent perturbations, possibly the disk ringing like a bell after the passage of a satellite galaxy. One such feature is the Monochoros ring, a ring of stars rippling around the outer disk. It might be debris from a swallowed dwarf, or simply a wave in the disk induced by a satellite's gravity. Using all these clues, astronomers have begun to sketch the Milky Way's history. In the beginning, over 12 billion years ago, our galaxy's progenitors were likely a few smaller protogalaxies, made mostly of hydrogen, helium, and dark matter. These clumps merged early on, building a stellar halo and the first, relatively small primitive disk. Many of the globular clusters formed in this era, either within the protogalactic fragments or in the nascent Milky Way. Then, around 10 billion years ago, a significant merger, Gaia Enceladus, delivered a load of stars to the halo and possibly created the thick disk by dynamical heating. Subsequent to that, the Milky Way spent the next several billion years evolving more quiescently. Gas continued to fall in, some perhaps from intergalactic filaments, some from smaller infalling dwarfs, and the thin disk grew outward, forming stars steadily. Our galaxy's spiral pattern likely persisted and perhaps reformed at times, and a bar may have formed a few billion years ago as the central disk became unstable and elongated. Minor mergers continued. Even today, the Sagittarius dwarf galaxy is being consumed, and the large and small Magellanic Clouds, our prominent satellite galaxies, are interacting with our halo and will eventually merge as well. Through all this, star formation has cycled on and off, enriching the interstellar medium further with each generation. The Sun's birth about 4.6 billion years ago came at a relatively calm time in the Milky Way's life, long after the major mergers, in a galaxy that already had a well-defined spiral structure and plenty of heavier elements. In a sense, our galaxy is a mosaic assembled from many pieces, some formed in-house, others acquired, and this process is ongoing. Even as we speak, the Milky Way is not done changing. It is surrounded by dozens of satellite galaxies, like the Magellanic Clouds and many ultra-faint dwarfs. Some of these will eventually merge into it. And looking to the far future, our galaxy itself is on course to merge with the Andromeda Galaxy, M31, some 4 billion years from now, an event that will drastically reshape both into a new, larger galaxy. The Milky Way's story is still unfolding, and we happen to find ourselves at a rather calm chapter in that long tale. In reading the stars and their motions, we have essentially become galactic archaeologists. We take the present evidence, the trajectories and elemental makeup of stars, and infer the past events that produce them. It's astonishing that here, on a little planet, we can piece together events that occurred 10 billion years ago and tens of thousands of light years away. And yet, piece by piece, we have done exactly that. The result is a narrative of construction and transformation. Our Milky Way grew by accretion and mergers. It has been both the cannibal and the cannibalized. It has swelled over time with the infusion of fresh material, and it continues to evolve. It remembers the violence and fireworks of its youth in the motions of old stars, and it wears the accreted stars of smaller galaxies as part of its halo, like scars or trophies. We have come far. From wondering what the Milky Way's band was in the sky, we have arrived at a point where we can describe its structure, its composition, its movement, and even its history. And perhaps, on some distant world orbiting a star on the far side of the Milky Way, there could be other beings looking up at this same band of light from their vantage point, asking similar questions. They too would face the challenge of understanding the Milky Way from within, unaware of our existence, just as we were long unaware of theirs. If such observers exist, then the mystery of our galaxy is a shared one, a grand puzzle that beckons to any creature with the will to look up and wonder. About 100 years ago, we didn't even know for certain that anything lay beyond the Milky Way. This very question was the subject of the Great Debate in 1920 between two leading astronomers, Harlow Shapley arguing that the Milky Way comprised the whole universe, Heber Curtis contending that the spiral nebulae were outside our galaxy, perhaps galaxies themselves. It was only in 1924 that Edwin Hubble measured the distance to the Andromeda Nebula and found it to be far, far beyond the Milky Way. In that moment, our perspective expanded immensely. The Milky Way was revealed to be just one of countless island universes. A large galaxy, yes, but hardly the only one. Our galaxy went from being the entirety of the cosmos to being one member of the local group, our small cluster of galaxies, similar in stature to Andromeda. Today, with modern instruments, we have even measured the mass of our galaxy and Andromeda. The Milky Way is approximately on the order of 1 trillion solar masses in total. That's 1,000 times the mass of our Sun. Though stars and gas are only about 10–15% of that. The rest is dark matter. Andromeda is of comparable mass and size, and contains perhaps 1 trillion stars to our few hundred billion. Knowing this places our galaxy in context. Not only is the Milky Way not the entire universe, it isn't even the biggest galaxy in our local neighborhood. Yet for us, the Milky Way is uniquely significant. It is home. When we gaze at that Milky Band, we are looking into the structure that made us. Our sun's existence, the heavy elements that form our planet and our bodies, the gentle environment that shelters life. All these are products of the Milky Way's long evolution. We owe our very existence to events that happened in our galaxy long before the Earth formed. Ancient supernovae that synthesized iron, for example. We are connected to the Milky Way profoundly. We are a part of it. To truly appreciate our galaxy, it helps to use more familiar analogies. To illustrate another way, imagine the Milky Way as an enormous city of stars. The spiral arms are like brilliant avenues, lined with hot young stars that shine like neon signs, bustling with nebula, where new buildings, stars, are under construction. The central bulge is a crowded downtown, full of old red giants that glow like streetlights in an ancient district. At the very center, a massive city hall, black hole, governs the motions around it. The halo forms the quiet suburbs, sparsely populated by a few old stars and clusters, far removed from the busy streets of the disk. Throughout this stellar metropolis, things are constantly changing. New structures rise, stars form, and old ones crumble, stars die. Sometimes a neighboring town, dwarf galaxy, gets absorbed into the city limits, adding its stars to our population. Yet despite all this hustle and transformation, the city of the Milky Way maintains its overall character through cosmic ages. We, living on Earth in a calm neighborhood, the Orion Spur, off one of the major arms, are citizens of this galactic city. We witness its grand traffic flow around us and participate in its story, even as we go about our humble lives. Galaxies are not static backdrops. They are active, dynamic systems. The Milky Way is an ecosystem of constant change, a cosmic forest in which stars are born, evolve, and die, enriching the soil, the interstellar medium, for the next generation. Stars form in the spiral arms, live their lives, the most massive burning out quickly, the smaller ones enduring longer, and eventually end, quietly if they are sun-like, dramatically if they are huge supergiants. When a massive star dies, it goes supernova. The explosion not only disperses heavy elements into space, but its shockwaves can jolt nearby gas clouds, possibly triggering the birth of new stars. This feedback loop, stars giving back matter and energy to the galaxy, is crucial. Through this feedback, the galaxy redistributes energy and matter and regulates its star formation. Stellar winds and supernova blasts carve bubbles in the gas, sometimes clearing out regions and halting star formation temporarily, other times compressing gas elsewhere and stimulating more star birth. It's a self-balancing act. At present, the Milky Way's star-making pace is relatively sedate. It converts only a few solar masses of gas into new stars each year on average, perhaps 1 or 2 new stars like the Sun, and a few more lower mass stars annually. By cosmic standards, this is a gentle rate. It's enough to keep the spiral arms adorned with some bright newborns, but not so high that we burn through all our gas quickly. There are starburst galaxies in the universe forming hundreds of stars per year, blazing furiously for short periods, and then quenching when their gas is exhausted or blown out. But our Milky Way seems to prefer a steady, sustainable cadence of star formation. This moderate behavior ensures that the Milky Way's gas supply will last many billions of years to come. Over time, each generation of stars changes the composition of the galaxy's gas a little more, enriching it with heavier elements. The young stars forming now carry within them the products of countless stellar lives before them. In this way, the galaxy's chemistry evolves, the metallicity of stars increasing as the cosmic soil becomes more fertilized. Our Sun, for instance, has far more heavy elements than the first generation of stars, telling us it formed in a used, enriched medium. This ongoing enrichment will continue with future generations. Meanwhile, the whole galaxy is gravitationally interacting with its environment. Our Milky Way is orbited by dozens of satellite galaxies. Some are fairly large, the Large Magellanic Cloud, and Small Magellanic Cloud, visible to the naked eye from the southern hemisphere, each a few percent the mass of the Milky Way. Others are extremely small and faint. The ultra-faint dwarfs discovered in recent years, some of which have only a few thousand stars. These satellites move around the Milky Way, and our galaxy's gravity pulls on them. Sometimes, as we've seen, it tears them apart, like the Sagittarius dwarf. The Large and Small Magellanic Clouds, LMC and SMC, are currently close by and interacting with our halo.
Their gravity may be raising tides in our disk and halo, and our gravity is stripping gas from them, producing the long Magellanic stream of gas that trails behind them. In recent years, astronomers have discovered more and more of these faint satellites. Dozens have been catalogued, and more continue to be found as our surveys improve. The Milky Way's entourage of satellites is more extensive than once thought. These interactions have effects. The LMC, for instance, with its substantial mass, around 10% of the Milky Way's mass, is tugging on our galaxy's halo and might even be shifting the center of mass slightly. It's likely contributing to the warp in our outer disk. Our disk is not perfectly flat, but bent, and the gravity of the Magellanic Clouds could be one cause of that warp. The infall of the Sagittarius dwarf seems to correlate with bursts of star formation in our disk. Indeed, some studies suggest that about 5 billion years ago, and again, about 1 billion years ago, Sagittarius's close passes perturbed our galaxy and triggered higher star formation rates, possibly even triggering the formation of our Sun around one such time. Thus, the satellites have likely influenced the Milky Way's evolution. Like dancers around a larger partner, their gravitational tugs send subtle ripples through the Milky Way's disk and halo. Our galaxy will continue to grow by merging these satellites. In the far future, as mentioned, it will experience the ultimate merger, with the Andromeda Galaxy, and likely also the Triangulum Galaxy, M33, a smaller member of our local group. In about 4 billion years, Andromeda and the Milky Way will draw together, their mutual gravity distorting both. Perhaps long tails of stars will be flung out, and over a couple of billion more years, they will coalesce into a single elliptical galaxy, sometimes dubbed Milkomeda. The night sky of Earth, if Earth is still around and life still here, would change drastically during that merger, with new patterns of stars and intense star-forming fireworks for a while. Eventually, the two spirals' identities will be lost in a new, larger galactic system. Thus, even the Milky Way is impermanent on cosmic timescales. Through all of this, one cannot help but feel a sense of narrative, a sense that the Milky Way has lived a life of its own. We, as sentient beings within it, have only just become aware of that grand story. It is a bit like coming of age and suddenly learning the history of your vast family or nation, except our nation is a galaxy 100,000 light-years wide and 13 billion years old. It took remarkable scientific sleuthing to deduce this history. It is a testament to the human mind's ability to reason and infer that we can reconstruct events so remote in time and space. Our map of the Milky Way, therefore, is not just a static picture, it's an unfolding story. It shows a current snapshot, spiral arms, bar, etc., but also contains clues of how that snapshot came to be. By studying other galaxies which we can see from the outside, we gain further insight into stages of our own. We see galaxies in various merger stages, or starburst phases, or with different proportions of components, and we realize the Milky Way likely went through similar phases, or will in the future. Our understanding of galaxy formation has, in turn, fed back to refine our model of the Milky Way. Mapping our galaxy from the inside has truly been one of humanity's great scientific achievements. Over the past century, we progressed from having only a vague idea of our place in the cosmos to having a detailed mental construct of our entire galaxy, something no one observer can ever see in full. It required meticulous data collection and clever deduction. It's as if we have mapped a vast labyrinth by walking through its corridors and feeling our way, since we cannot rise above it to see the whole. And somehow, we succeeded. Mapping our galaxy from within stands as a triumph of human curiosity and intellect. Even as we gather more data and refine our models, we remain observers trapped inside the system we study. We will always be looking outward from within, and that inherently limits our perspective. There may always be features we cannot perceive directly, perhaps some subtle pattern in the distribution of stars that is too broad to recognize from inside, or some effect that requires an external view. We compensate with ingenuity and indirect methods,
But there is something profound about this limitation. We are part of the very thing we are trying to understand.
It is interesting to note that while we cannot see our galaxy from outside, observers in other galaxies can. To an astronomer in the Andromeda galaxy, for example, the Milky Way would appear as a faint, elongated spiral nebula in their sky, much like Andromeda appears to us. They could capture photos of our galaxy's grand design in a way we cannot. And conversely, we see Andromeda's spiral structure clearly, while the Andromedans, if any exist, must deduce it from the inside. In a cosmic sense, we and Andromeda serve as mirrors for each other. By studying other galaxies, we've come to understand our own, and in the future, the Milky Way and Andromeda will merge and no longer be separate, their destinies entwined. In about 4 billion years, as mentioned, this merger will begin, an event that future astronomers, perhaps not human, perhaps whatever beings exist then, will witness and record. The Milky Way as we know it will evolve into something new. But those changes are far in the future. For countless generations to come, the Milky Way will remain the majestic barred spiral that cradles our sun and its planets. Our explorations have transformed that misty band in the night from a source of speculation and myth into a mapped and modeled galactic system. Yet, even as we explain it scientifically, the Milky Way has lost none of its ability to inspire awe. If anything, knowing what it truly is makes it more amazing. The simple band of light has become a vast spiral of stars in our mind's eye. The tiny points of light have become distant suns with their own worlds. The dark gaps have become nurseries holding unborn stars. The slight glow on the horizon of vision has become the memory of ancient mergers and the halo of an invisible mass. So the next time you find yourself under a truly dark sky, take a moment to let your eyes wander along the Milky Way's gentle glow. Think of all the stars hidden in that band, the clusters and nebulae, the spiral arms wrapping around, and the far-off center with its secrets. Consider the journey that light has made to reach you, and the journey we have made to understand what it means. In that quiet moment, you are connected to our galaxy in a profound way, an observer within it, aware of its vastness and complexity. Think of how many before you have stood under this same sky, seeing that milky arc and wondering what it was. Now you carry the answer to their wonder. The Milky Way is our home galaxy, breathtaking in its scale, dynamic in its story, and you are a part of it. The hazy band of light ceases to be just an appearance. It becomes a personal encounter with the cosmos, a bridge between you and the ancient, ongoing story of our galaxy. It is a reminder that even as we strive to explore and understand the universe, we are already deeply home within it, nestled among the stars of the Milky Way, forever looking out and in.